Somewhere on the internet, people keep talking about a strange place in space. A huge, empty region in the constellation Boötes. They say it's almost completely empty. No stars, no bright galaxies. Just darkness, stretching for hundreds of millions of light years. Some videos call it a cosmic scar. Others joke that it's a bug in the universe. And there's a popular idea that if you somehow fell into this place, you would keep falling forever, drifting through nothing until the universe itself ends. That sounds like science fiction. But the reason this rumor exists is actually very real. In the early 1980s, astronomers started making three-dimensional maps of the universe. Instead of just looking at the sky, they measured how far galaxies really were. And that's when they noticed something unexpected: huge dark regions. Not because the data was missing, but because there were almost no bright galaxies there at all. This discovery completely changed how we see the universe. It turned out space isn't filled evenly with stars and galaxies like in movie posters. It's more like a giant web, with crowded regions and enormous empty spaces in between. So, here's the real question. If you were floating inside the biggest empty region we know, what would actually happen? Would you fall? Would you feel anything? How would time pass? And what would it do to your mind when there's almost nothing around you? In this video, we're going to break the myth down step by step. Using real science, real discoveries, and simple explanations, we'll explore what falling into the biggest void in the universe would really be like, and why it changes how we think about space and about ourselves. Before we talk about what it feels like to drift through a region almost empty of galaxies, we have to go back to the years when the universe itself first had to confess that it was not the smooth, comfortable backdrop we thought it was. It began, oddly enough, with a hiss in an antenna. In the early 1960s, at a research site in New Jersey, two radio engineers named Arno Penzias and Robert Wilson were trying to be rid of a problem. They were working with a large horn-shaped antenna at Bell Labs, designed to listen for faint signals bounced from communications satellites. Instead, their instrument kept hearing a soft, stubborn noise, a kind of uniform hiss that would not go away. They checked everything human first. They recalibrated the electronics. They looked for faulty cables. They pointed the antenna in different directions. There was even a famous, almost comic scene where they climbed inside the horn and cleaned out pigeon droppings, just in case the birds were somehow to blame. When they turned the instrument back on, the noise was still there. Same strength, same character, same whisper, no matter where they pointed. On May 20th, 1964, after months of testing and retesting, what they had really been measuring became clear. A faint bath of microwave light that filled the sky from every direction with almost the same intensity. It would later be called the cosmic microwave background. The afterglow of the early universe cooling and stretching as space itself expanded. For cosmologists, that hiss was not just a curiosity. It was a message from a time when the universe was young, hot, and astonishingly dense. The pattern and temperature of that background light told them that space had once been more uniform than it is now, and that it had been expanding for billions of years. The universe, it seemed, had a childhood. It had a history. It was not a static, eternal stage with stars nailed in place. Once you accept that the universe has a past, another question follows almost automatically. If it began in a nearly uniform, hot plasma and has been expanding and cooling ever since, what does it look like now when you zoom all the way out, not from one backyard or one galaxy, but on the largest scales we can map? Does it still behave like the neat, evenly sprinkled wallpaper of stars that our intuition likes to imagine? For a long time, all we had were two-dimensional projections. Astronomers could look at the night sky, measure the positions of galaxies as dots, and make catalogs. But without real distances, it was like looking at a crowded photograph of a city's skyline, with no sense of which building is nearer or farther. The sky was a flat dome. Depth was guesswork. In the late 1970s, that began to change. A team at the Harvard-Smithsonian Center for Astrophysics started a systematic effort to measure not just the positions of galaxies, but also how fast they were moving away from us. They did that by looking at the redshift of each galaxy's light, the way familiar spectral lines were stretched toward the red end of the spectrum as the universe expanded. From that stretching, combined with the Hubble relation between distance and recession speed, they could estimate how far away each galaxy was in 3 dimensions. It sounds dry on paper catalog galaxies, measure redshifts, tabulate values, but the emotional moment did not live in the tables, it lived in the plots. As the data from what would be called the first CFA redshift survey accumulated, astronomers began to put their galaxies into a kind of 3-dimensional map. Imagine a thin wedge of the universe, like a slice of cake, with the Earth at the narrow end, and each galaxy placed at the appropriate distance along its direction in the sky. When those points were first charted, something strange emerged. The galaxies were not scattered like a fine mist. They clumped, they lined up, they traced strands and walls. And between those strands and walls, gaps. Not little gaps you could ignore, but enormous, yawning regions almost empty of bright galaxies. When the first significant batch of CFA data was presented around 1982, the picture was crude by modern standards, but the pattern was unmistakable. Instead of fog, there was foam. The galaxies seemed to prefer the surfaces of what looked like huge, roughly spherical bubbles, leaving the interiors thinly populated. The places where multiple bubbles met formed denser knots and filaments, like the joints in a spider's web. The empty parts were given a simple name: voids. A few years later, as more redshifts were added, the CFA team released a now iconic diagram, sometimes called a slice of the universe. It was published around 1986 and showed a much thicker wedge filled with thousands of galaxies. That image is still startling to look at. A thin triangular patch that begins in a clump at the tip and then blooms into a mottled pattern of arcs and branches and hollows. Once you see it, you cannot go back to the poster version of the cosmos as a smooth, dense star field. The galaxies outline structures that span hundreds of millions of light-years, while equally large regions in between have almost none. The best analogy is not a cloud of dust, but a piece of sponge or bread, where matter collects in the strands and crust, and much of the volume is air. The quiet revolution here was not in the mathematics. The idea that gravity should amplify small irregularities and create rich structure from tiny initial fluctuations was already built into cosmological models of the time. What changed was that, for the first time, humans saw an observational map where that logic was drawn in real positions. It was no longer a thought experiment, it was a chart. To make such a chart, astronomers did not need exotic technology beyond the telescopes and spectrographs already in service. They needed patience and a clear understanding of what redshift really encodes. When light leaves a galaxy and travels through an expanding universe, its wavelengths stretch as space stretches. The more expansion that has occurred while the photon is in flight, the longer, and therefore redder, the wavelength becomes by the time it reaches us. By measuring exactly how much familiar spectral fingerprints are shifted, you get a handle on how far the light has traveled, and thus how far away the galaxy is. In simple terms, redshift gives 2 things at once. It tells you how fast a galaxy is receding and, under a cosmological model, how distant it is. That dual role is what lets astronomers turn the flat dome of the night sky into something more like a relief map, where valleys and ridges correspond to underdense and overdense regions of space. On the page, those distances are just numbers in columns. In the mind, as soon as you plot them, they change the way you picture existence itself. If you grew up with the idea that space is packed with stars almost everywhere, that a trip in any direction would take you past countless suns, the CFA maps feel almost rude. They say, no, most of the volume of the universe is not like your sky. There is a kind of cognitive dissonance in that. Our senses evolved inside a galaxy, on a planet that orbits an ordinary star in a fairly typical spiral disk. We look up from that position and see a rich, textured band of light, a Milky Way that makes it easy to believe the universe is thick with structure. We forget that this is exactly what you would see if you happened to live on one of the rare, dense strands of the cosmic web. The CFA plots pull the camera back and show the context thin threads of brightness separated by great absences. It is tempting to think of those absences as mistakes, as if the universe began to draw a pattern and then got bored and left blank space between the good bits. But the simulations tell another story. When cosmologists take the initial tiny irregularities seen in the cosmic microwave background and let them evolve under gravity and expansion, the same sponge-like pattern appears. Regions that are just slightly denser than average pull in more matter over time. Regions that start out slightly underdense lose matter to their neighbors. The web and the holes in it grow up together. The first generation of three-dimensional maps made this interplay visible in a way that theory alone could not. In the mid-1980s, as other surveys joined and extended the CFA work, astronomers began to catalogue voids with the same seriousness they gave to clusters and superclusters. It was no longer enough to talk about where galaxies are. One had to talk about where they are not. For ordinary viewers seeing those maps in popular articles, a more visceral shift happened. Space stopped being the infinite star field of planetarium shows and science fiction art. It started to resemble a structure with texture, thick in some places, almost bare in others. The familiar night sky on Earth, crowded with points of light, turned out to be a local illusion, like standing in a forest and believing that all land is forest because trees fill your horizon in every direction. If you think of the universe in poster form, you might picture yourself as one speck lost in a glowing sea of other specks. If you think of it in survey form, you begin to see yourself as part of a narrow, fragile filament stretched across a deep darkness. The psychological weight of those two images is not the same. By the time the slice of the universe diagrams had circulated through conferences, journals, and then into books and documentaries, one question kept resurfacing, almost as a nervous joke. Those huge holes in the map, what are they, really? Are they just statistical quirks, places where the survey happened not to catch many galaxies? Or are they genuine underdensities in the fabric of matter? How large can such a void be and still fit within our standard picture of cosmology? Underneath the technical debates, a more personal curiosity simmered. If you could somehow place yourself inside one of those empty regions, far from the walls of galaxies, what would the universe look like from there? How would the sky change? How would distance feel when almost all landmarks fall away? During the middle of that decade, one particular patch of sky, in the direction of the Herdsman constellation, began to stand out in the data. The more astronomers probed it, the quieter it seemed. Fewer bright galaxies. Then, fewer still. A region so underpopulated that it strained the imagination. Even in a universe that had already admitted it was mostly made of space, it would eventually earn a name and a kind of reputation, as if the cosmos itself could have a missing piece. But before that story took shape, it was just one more gap on a redshift plot, an absence that dared people to ask what it means for something as large as a universe to have places where almost nothing chose to gather. In that one direction, toward the quiet patch in the Herdsman of the sky, the gap on the map slowly stopped being just negative space and began to feel like a place defined not by what was there, but by how stubbornly almost nothing showed up. Boötes is not an especially dramatic constellation to the naked eye. On a clear night, it is a modest figure, a herdsman leading the curve of the Big Dipper. But in the 1980s, when astronomers pushed their redshift surveys deeper in that direction, they stumbled onto something that did not match the rest of the sky at all. At roughly 700 million light-years from Earth, they found a roughly spherical region in which bright galaxies were strangely scarce, a hollow in the cosmic web that would come to be known as the Boötes Void. Robert Kirshner and his collaborators were not hunting for a legend. They were extending their earlier work, measuring the recession speeds and positions of galaxies to fill out the three-dimensional map. In the data published around 1981, they noticed that over a huge stretch of redshift space in that direction, their samples simply went quiet. There were galaxies on the near side. There were galaxies on the far side. But across a swath corresponding to hundreds of millions of light-years, there were almost no bright galaxies at all. When the size was estimated, the numbers did not feel modest. The void's radius was put at about 62 megaparsecs, which translates to nearly 200 million light-years. That means that if you could place the Milky Way at its center and then sprinkle copies of our galaxy throughout that sphere at the average cosmic density, you would expect to fit a couple of thousand of them comfortably. Instead, careful counts turned up only around 60 galaxies, scattered sparsely through a volume where, by all rights, there should have been many more. Later work using infrared selected samples refined the picture rather than dismissing it. Surveys based on the infrared astronomical satellite focused on dusty, star-forming galaxies that might have been missed in optical catalogues. Even then, within the region defined as the Bootes Void, only a small handful of such galaxies appeared. One detailed study found roughly a dozen infrared galaxies in that space, and only a few of those belonged to a complete, well-defined sample. The conclusion was not that the void was empty, but that its galaxy density was depressed by a factor of several compared to the surrounding universe. For astronomers who lived in the world of numbers, this was something that could be worked into models and statistics. But as soon as the story escaped into popular science writing, the language changed. Writers called it a great void, a cosmic hole, even a great nothing, as if space itself had been gouged out. Some magazine articles spoke of it as a kind of scar, a missing patch on the otherwise mottled skin of the universe. The name supervoid entered circulation, and with it came associations that the data alone never claimed. The human mind tends to treat absence as an event. A missing tooth draws the eye more quickly than a row of healthy ones. A burned patch on a hillside seems more meaningful than the acres of green around it. In the same way, the Bootes Void became a magnet for metaphor. People joked about a bug in the cosmic program. Others half-seriously wondered if it might be a sign of something exotic that had happened in the very early universe, a signature left behind by physics beyond our standard picture. In the technical literature, the questions were more restrained. Could such a large underdensity arise naturally as part of the growth of structure in a universe governed by cold, dark matter and dark energy? Or did its size and depth hint at some rare event in the initial conditions, something like a topological defect or a cosmic texture, imprinting itself on the density field? Papers compared simulations with observations, asking how common a void of that scale should be if the standard cosmological model is right. The answers landed in a gray zone. Unusual, yes. Impossible, no. The Bootes Void did not stay alone for long in our catalogue of unsettling absences. As instruments improved and surveys widened, cosmologists began to notice other hints that underdense regions could leave their fingerprints on the universe in subtle ways. One of the most discussed examples lies not in a map of galaxy positions, but in the temperature pattern of the cosmic microwave background itself. When the Wilkinson Microwave Anisotropy Probe released its full-sky maps of the microwave background in the early 2000s, cosmologists noticed that, amid the familiar speckled pattern of hot and cold spots, there was a particularly large and unusually cold patch in the southern sky, in the direction of the constellation Eridanus. It came to be known simply as the cold spot. Later, the Planck satellite saw the same feature, confirming that it was not an artifact of a single instrument. Most of the tiny temperature fluctuations in the microwave background can be explained as the imprint of early density variations stretched and projected onto the sky. The cold spot, however, is larger and colder than those fluctuations typically are. One possible explanation within standard physics is that photons from the background pass through a very large, underdense region on their way to us, a supervoid whose evolving gravitational potential slightly drained their energy via what is called the integrated Sachs-Wolf effect. If that is the case, the cold region on the sky would be, in part, a shadow cast by a void. Teams have searched that line of sight using galaxy surveys, and they do find evidence of underdense regions and extended supervoids in the general direction of the cold spot. But the match is not perfect, and the statistics are subtle. Some analyses suggest that the voids are not quite large or deep enough to fully account for the anomaly. Others argue that, taken together, they may still play a major role. The debate is ongoing, and the cold spot remains a kind of Rorschach test for cosmologists, a place where people project their hopes for new physics or their confidence in the robustness of the current model. Seen from a distance, then, the Bootes Void and the cold spot belong to the same family of questions. They both force us to confront something uncomfortable about our instinctive picture of space. We are used to thinking of the universe as full of stars, full of galaxies, full of clusters and filaments. When we do concede emptiness, we usually treat it as the boring in-between, a neutral background that does nothing and means nothing. Yet here are cases where less than average becomes a feature in its own right, where a deficit of structure shapes what we see and how light moves. It is important to be clear about what these supervoids are not. They are not holes punched in the universe. They are not regions where physics turns off, or where matter has been scraped perfectly clean. In the Boötes void, there is still gas, still dark matter, still the faint glow of galaxies scattered through the volume. The matter density is low compared to the cosmic mean, but not zero. Gravity still works there. The laws of motion are the same. To call it a void is a convenience, not an admission that the universe somehow failed to show up. Nor are these regions anything like the compact, intense objects that truly trap matter and light. A void does not pull you in. If anything, it is the opposite, a place where there is less gravitational pull than usual, because much of the mass has gathered elsewhere. To travel through a void is not to be swallowed. It is to move through a slightly easier gradient, a region where the usual tug of nearby galaxies is weaker. The language of falling betrays us here. When people say you could fall into the Boötes void and never stop, it sounds as though there is a bottom, a destination, a center that is doing the pulling. In reality, the edges of a void are where most of the mass is. If you let gravity alone decide your fate, you tend to drift away from the underdense interior and toward the denser filaments and walls that surround it. The void itself does not grab you. It simply fails to hold you in place. So why does the idea of falling into such a region persist? Part of it is scale. A sphere nearly 200 million light-years across is so far beyond human travel or even human lifetime that it feels like a kind of endlessness. If you set off toward one side from the center at an ordinary fraction of the speed of light, countless generations would live and die before your descendants saw the galaxy walls loom large. In that sense, you would indeed fall forever, not because the void is infinite, but because you are finite. Another part is the visual. When artists and animators try to depict the Boötes void, they often draw a glowing web of galaxies with a vast, dark hole punched out. It is a compelling picture, but it encourages the wrong intuition that voids are like gouges or tears. The real universe is softer than that. The transition from wall to underdensity is gradual. The borders are fuzzy. There is no sharp edge where something suddenly stops and nothing begins. From the standpoint of physics, the Boötes void is an extreme example of a pattern that pervades the universe. Matter clumps, and in clumping, it leaves other regions depleted. From the standpoint of an observer trying to picture themselves there, it is something stranger. A place where, for hundreds of millions of light-years in every direction, the usual landmarks thin out, where the bright threads of the web are far away on every side, and you are left with a sky in which the familiar richness of clustered galaxies has been replaced by a few lonely smudges. Standing at the center of that thought experiment, the question that began as a scientific curiosity changes tone. It is no longer just, how big can a void be? Or how does it fit into our models? It becomes, what does presence mean when almost everything is far away? What does it mean to say you are in a universe, if for a very long time, in every direction you look, the universe barely appears? If you take seriously the idea of being there not as an explorer, not as a survivor of some imagined disaster, but simply as a conscious pattern that happens to find itself far from most other patterns, another, quieter question comes up. In such a place, what would the sky look like? What would falling into the void amount to, if not plunging toward a center? Those are not questions you can answer with a single diagram or a single number. They require a closer look at what fills even the emptiest regions, how gravity behaves when it has very little to work with, and how light from distant galaxies stitches a sparse sky together. To understand what it means to be at the heart of a supervoid, we have to turn from the map back to the physics, and from the word empty back to the details of what, quietly, remains. What remains is thin and quiet, but it is not nothing. And if we get this wrong, everything that follows will feel like a ghost story instead of a description of where we actually live. The first illusion to drop is simple. Nowhere in the observable universe has been scrubbed clean of matter, energy, or fields. There is no cosmic delete key that has been pressed on any region of space. Even in the most dramatic voids that astronomers have mapped, what you find is not a hole torn in reality, but a place where the usual contents are diluted. Start with the most obvious absence, bright galaxies. When cosmologists define a void, they usually mean a region where the density of such galaxies is much lower than the cosmic average. In the Boötes void, for example, the number of luminous galaxies per unit volume is depressed by roughly an order of magnitude. If you only count the kinds of systems we can see in ordinary optical surveys, then yes, a void looks close to empty. But starlight is a biased tracer of what exists. It notices only the hot, dense knots that have managed to light up. In between those knots, even in the darkest regions, other ingredients remain. There is gas, for one thing, not the thick clouds that form stars inside spiral arms, but intergalactic gas, thinned to almost inconceivable levels. A cubic meter might contain, on average, far fewer atoms than a laboratory vacuum on Earth. Stretch that gas out over scales of millions of light years, and it becomes a tenuous medium that can still scatter and absorb light, carry heat, and respond to gravity, even if it is practically invisible to our eyes. Threaded through and around that gas is dark matter. It does not shine or absorb. It reveals itself only by its gravitational pull. In the standard cosmological model, most of the matter in the universe is of this unseen kind, and it forms the underlying scaffolding of the cosmic web. In simulations where cosmologists let cold dark matter clump under its own gravity, starting from tiny initial fluctuations, the same network of filaments and voids appears that we see in galaxy surveys. Within those voids, the dark matter density is indeed lower than average, but it is not zero. The voids are not cavities in the dark matter distribution. They are basins where the density has been drained, not erased. You can picture it the way you might picture bubbles in bread. The dough is the dense regions where galaxies and clusters eventually form. The air pockets are the voids. Inside the air pockets, there is still air. There are still molecules, still thermal motion, still chemistry. What is missing is only the thicker, heavier material that has been drawn away. On top of gas and dark matter, there is also light. Not just occasional photons from stray galaxies, but a constant bath of radiation that pervades all of space, the cosmic microwave background. Those microwaves were released when the universe was very young and hot, at a time when protons and electrons first combined into neutral atoms and the fog of charged particles became transparent. From that moment on, the photons have been traveling largely unimpeded, stretched to longer wavelengths as space expanded. When Arno Penzias and Robert Wilson picked up that faint hiss in their horn antenna in the early 1960s, they were not listening to a local phenomenon. They were hearing a glow that fills every direction to almost the same intensity. That glow does not care whether you are in a galaxy cluster, a filament, or the center of a supervoid. The temperature of the microwave background changes only very slightly from place to place, so every region of the universe, including the interior of Botez Void, is soaked in this ancient light. There is something quietly humbling in that. Even if you could strip away every nearby galaxy, every recognizable structure, you would still be standing in a kind of echo chamber of the early universe, bathed in relic photons that have been traveling for more than 13 billion years. Emptiness, on that scale, means an absence of local decoration, not an absence of history. The way voids form in simulations makes this idea more concrete. Cosmologists run N-body codes on supercomputers, in which they track the gravitational evolution of many particles representing dark matter. They start from a nearly uniform distribution, slightly perturbed according to the fluctuations observed in the microwave background. Then they let time run forward under gravity and cosmic expansion. The particles fall toward one another, form filaments and knots, and leave behind regions where the density drops. In that picture, voids are not special objects that have to be put in by hand. They are the natural side effect of clustering. Where random initial fluctuations happen to be a little denser than average, matter flows in and builds up structures. Where the fluctuations were slightly underdense, matter flows out, leaving behind a basin that empties further with time. The universe, in a sense, accentuates its own contrasts. Bright regions get brighter, sparse regions get sparser. If you want an analogy that does not involve equations, think of a young city. At first, a few market stalls appear at a crossroads. That slightly denser gathering of people attracts more trade, more houses, more streets. Meanwhile, stretches of land a little farther away see less traffic. Over the years, the crossroads grows into a town, then a city. The quiet lots outside are not cursed or cut off. They are just the places that fewer people chose to settle. And as the city grows denser in its core, those outskirts feel more and more like empty space. The cosmic web behaves in a similar way, but it has no planners and no intentions. It has only gravity. The gravitational wells created by growing clusters and filaments tug material from their surroundings, including from the neighboring underdense patches. Those patches are the cosmic equivalent of land that no one built on. The longer structure formation continues, the more pronounced the distinction between the built-up regions and the voids becomes. When astronomers tune their simulations to match observations from surveys like the original Harvard-Smithsonian maps, the Sloan Digital Sky Survey, and others, voids appear naturally with sizes and depths broadly similar to those we see. That is one reason cosmologists are generally comfortable treating even supervoids as part of the normal life of a universe dominated by cold, dark matter and dark energy, rather than as evidence of some radical new physics. None of this changes the psychological impact of the word void. In everyday language, void suggests absolute nothingness, a place where not only matter, but even the rules have gone missing. Physics does not really offer such places. Quantum fields thread all of space. Gravity acts everywhere. The vacuum of intergalactic space is full of virtual activity. Even the regions we call vacuum in the lab are seething compared to the mean densities between galaxies, and those regions are, in turn, full compared to the deepest cosmic voids. There is no scale at which the idea of a perfect, sterile, featureless nothing is realized. What we have instead are gradations. More structure here, less there, denser here, thinner there. When we talk about falling into a void, we are not talking about crossing a boundary into non-existence. We are talking about moving from one kind of environment to another, from a region where matter has been busy building stars and planets and nebulae, into a region where matter has mostly passed by, leaving only a faint residue. That distinction matters for the thought experiment that runs quietly under this whole story. If voids were truly nothing, to enter one would be to leave the universe behind. There would be no gravity to speak of, no background radiation, no passing photons from distant structures, no medium at all. The experiment would end immediately, because there would be no way to define position, motion, or time. You cannot drift in a place with no fields. Instead, our traveler remains very much inside the universe. They carry their own gravitational influence, however tiny. They are surrounded by the same microwave bath as everyone else. Distant galaxies still send light their way, albeit faint and sparse. Dark matter still curves space around them, even if its density is lower than average. Their atoms still vibrate. Their clock still ticks. In fact, from the standpoint of pure physics, nothing dramatic happens as you cross from a filament into a void. There is no sharp edge, no sudden drop in density that would register as a shock. The change is gradual, spread over tens of millions of light-years. The local expansion of space becomes a little more dominant as the pull of nearby structures weakens. The mean gravitational potential becomes shallower. If you calculate the motion of a test particle, you find that its trajectory is subtly different from what it would be in a more crowded region. But there is no cliff, no absolute threshold. The drama, if there is any, lives in the contrast between our expectations and this reality. We tend to equate presence with safety. To feel surrounded is to feel held. To see crowded starfields is to believe that the universe is busy in our neighborhood, that we are located in one of the main rooms of the house. Voids undermine that intuition. They remind us that most of cosmic space is more like the unbuilt outskirts of the city than its center, and that even our own galaxy, rich as it looks from within, sits on a narrow strand stretched across a larger emptiness. You could say that the universe is not so much a fullness dotted with gaps as a near emptiness decorated with a few threads of matter. From that perspective, falling into a void is less a special fate and more a delayed recognition of what was always true, that structure is the exception, not the rule. It is worth pausing on one more ingredient before we turn to the traveler. Dark energy, the mysterious component of the universe that drives its accelerated expansion, does not clump the way matter does. Its density, as far as current observations reveal, is roughly uniform in space. That means that in a very real sense, voids are where dark energy dominates most cleanly, because there is less ordinary and dark matter around to compete with it. In dense regions, gravity from matter can locally slow or even temporarily reverse the expansion, binding things into galaxies and clusters. In voids, with less matter to resist, the global tendency of space to expand can express itself more freely. That has consequences. Over very long timescales, underdense regions tend to expand a bit faster than the cosmic average. They effectively grow emptier, pushing their sparse contents toward the surrounding walls. So a void is not only a snapshot of where matter is scarce, it is a dynamic environment where the balance between gravity and expansion leans even more toward expansion than usual. Again, this does not create a special sensation for any particular observer. You do not feel space stretching under your feet, but it shapes the slow evolution of distance. It means that if you release an object in such a region with no special initial push, it will, over time, find itself moving away from other free objects, dragged along by the general flow. Put all of this together, and the picture inside a void gains texture. There is a thin gas, far more diffuse than any vacuum you have stood in. There is dark matter, sketching out a low-contrast version of the cosmic web. There is the ever-present microwave background, a nearly uniform glow from the early universe. There is dark energy, quietly encouraging space to expand. There is starlight from distant galaxies at the boundaries, arriving as faint smudges on an almost black sky. And there is you, or your imagined spacecraft, not erased, not outside the universe, but embedded in this subtle sea. Seen this way, the move from galaxy to void is not a step into non-existence. It is a shift in ratio. Less local structure, more global background. Less obvious company, more reliance on signals that have traveled for enormous stretches of time. That is the stage our thought experiment needs. Not a nightmare fall into nothing, but a long drift into a place where the universe is still fully present, just less decorated. Now that the interior of a void has stopped being a blank in our minds, we can ask a more precise question. If you were carried out from the busy disk of a galaxy and released into the middle of a supervoid, what would that gradual thinning of structure feel like? Not to your instruments, but to your sense of motion, of sky, of belonging. The question turns from a map into a corridor. It is no longer what is inside a void, but what does it feel like to let your whole frame of reference slip toward that kind of place? So take a small craft, not sleek, not dramatic, just a sealed room with enough technology on board that biology never needs to enter the story again, air that never runs out, heat that never fades, a quiet engine that can give you a push and then stay silent for the rest of time. Outside, there is only the disk of your home galaxy, and, far beyond it, the fine lattice of the cosmic web. In this thought experiment, the details of the hull do not matter. Only two things do. First, that you are free from every ordinary constraint that would normally end a journey long before it reaches intergalactic scales. Second, that once the initial push is given, you stop firing the engine and simply coast. No more noise, no more thrust. Just your craft sliding through the large-scale structure of the universe along a path you chose. The direction you choose is one of those underdense basins that astronomers would call a supervoid, the center of a region like the Botes Void, where the galaxy density is dramatically lower than average. You begin near the familiar, somewhere out in the suburbs of the Milky Way, and you set your course so that, in the coordinates of cosmology, your peculiar velocity is aimed directly toward the void's heart. At the very beginning, nothing about the sky feels different. Through whatever windows or cameras your vessel has, the Milky Way still dominates one side of the view as a thick band of light, scattered with dust lanes and clusters. The nearest companion galaxies, small satellites, and the larger spirals beyond are where they have always been. The constellations drawn by the bright stars of your home sky have not yet broken apart. You fire the engine for a while, long enough to reach a speed that would be unimaginable for any current spacecraft, but still shy of the speed of light. Then you turn it off. From this moment on, you are not pushing against anything. You are in free fall, in the gravitational sense, carried by your initial velocity and by the general expansion of space itself. Inside the cabin, that is a difficult state for a human nervous system. On Earth, motion is something you feel through friction and contact. Acceleration presses you into cushions, braking leans you forward. Even in orbit, astronauts train themselves to trust their instruments because their inner ear has so little to work with. Out here, between galaxies, there is no air rushing past, no rumble of wheels, No rail or road to fix your frame. Without windows, you would have no sense of movement at all. The brain dislikes that silence. It tends to translate any change in the view outside into a story of falling, even when there is no surface to fall toward. As the Milky Way very slowly shrinks behind you, you would be tempted to say you are dropping away from it, sliding down some invisible slope. The physics is more prosaic, you are simply coasting, while the gravitational pulls of all the mass around you, including your home galaxy, continually adjust your path. For a long time, the change in the sky is subtle. The first stretch of your journey, measured in tens of millions of light years, still keeps you in a region where galaxies are relatively common. The Milky Way fades from a structured, bright band into a thinner streak, then into a compact, milky patch, something like a distant, unresolved cluster. Other nearby galaxies that once sprawled across your field of view become isolated points. You can think of this phase the way you might think of leaving a city by train at night. At first, the windows are filled with dense lights, shops and towers and traffic. Gradually, the tall buildings fall away, street lamps thin out, a few farmhouses slide by. What changes is not that light vanishes entirely, but that it arranges itself into smaller, more separated islands. On cosmological scales, that thinning continues, in a way no train ride ever could. After you have covered a distance that light itself would take hundreds of millions of years to cross, the familiar signature of a galaxy cluster becomes rare. In surveys, astronomers describe voids by saying that their galaxy counts fall well below the mean within a certain radius. For you, that statistic translates into something more immediate. You pass through regions of sky where the density of bright smudges is palpably lower. If you had access to a navigational display that overlaid your position on a map derived from something like the Sloan Digital Sky Survey, you would see your trajectory leaving the bright spaghetti of filaments and drifting into one of the pale, almost empty cells between them. Scientists sometimes render this in visualizations, letting a virtual camera fly through the simulated universe. The effect, even on a screen, is striking. Points of light stream past, clustered in strands, and then, suddenly, they do not. The camera glides into a volume where the dots are few and far between, and for a while, it is like sailing through a sea at night, with only a handful of distant ships visible on the horizon. In your cabin, there is no soundtrack. Only the slow change in the pattern of stars and galaxies tells you that you have left the crowded neighborhood and entered the outskirts. The Milky Way, once a dominating presence, has shrunk to an object so small that it might be mistaken for any other distant spiral. Eventually, it becomes a dot among dots, and only your instruments remember which one it is. Behind you and around you, the motions of all those galaxies continue to obey the same expansion law that astronomers describe with the Hubble constant. Distances between unbound objects increase over time, on average. On top of that smooth expansion, each galaxy, each cluster, each void has its own local flows, small deviations from the ideal called peculiar velocities. Your own initial push is one such peculiarity. The void you are entering has another underdense regions, over long periods, tend to expand slightly faster than the cosmic mean because there is less matter inside them to slow the expansion down. You do not feel that. There is no sense of a wind picking up as you cross some invisible border. But the mathematics notes the difference. Relative distances inside the void grow a little more quickly. Its interior gradually evacuates. You and your craft, if left entirely to the combined influence of gravity and expansion, would slowly drift toward the higher density walls that surround the void. For the purpose of this thought experiment, though, you are allowed a very gentle correction thrust now and then, just enough to hold you roughly near the geometric center as the structure evolves. From that vantage point, time stretches. You can stay there for as many subjective years as you like and the sky will barely shift. The walls of the void are so distant that even light takes hundreds of millions of years to cross from them to you. Any proper motion of the galaxies that live on those walls, any merging or rearranging they do, is smeared out into changes too slow for one lifetime to register. What you can notice is the contrast between different directions. If the void is not perfectly spherical, and real voids rarely are, there will be parts of your sky where the nearest filaments are somewhat closer, and others where they are more remote. In the former, the faint fuzz of galaxy clusters may be fractionally brighter, their apparent angular size a little larger. In the latter, the clusters are smaller, dimmer, more tightly packed into a small patch of sky. Your vessel's detectors, if sensitive enough, could also pick up the glow of the intergalactic medium-thin gas, warmed to different temperatures, emitting in ultraviolet or X-rays, tracing the hidden scaffolding of dark matter. Even within the void, there will be slight variations, places where a tenuous thread of gas and dark matter runs through, barely luminous, almost imperceptible without careful integration. The void is underdense, not uniform. Inside your own cabin, the absence that presses in is not physical pressure, but lack of reference. On Earth, every movement of the sun across the sky, every passing plane, every familiar constellation provides orientation. In a galaxy, the asymmetric light of the disk, the shape of the spiral arms, the clear presence of a galactic center all act as anchors. Out here, in the middle of a supervoid, the anchors are too far away to pull much on your intuition. You could spin the craft to create artificial gravity and to settle your body's discomfort, but that would not change the view outside. The galaxies on the walls of the void would not sweep past like streetlights. They would hang almost motionless. Over eons, the redshifts of their light would slowly increase as the universe expands. Spectral lines would slide, very gently, to longer wavelengths. That drift, measured carefully, would tell you that space between you and them is stretching. But again, it would be a conclusion drawn from data, not from any direct sensation. One of the few constants in this landscape is the cosmic microwave background. Your instruments would register it as a nearly perfect blackbody spectrum at a temperature of a few degrees above absolute zero. The slight anisotropies, the tiny hot and cold spots, imprinted by early density fluctuations and later integrated effects, would still be there. Moving to the center of a void would not turn that background off. At most, it would slightly alter the pattern of the anisotropies due to your changed gravitational environment and peculiar velocity. You would still be bathed in the same primordial light that Penzias and Wilson heard humming in their antenna on that May day in the mid-1960s. Every now and then, you might pass a lonely galaxy that happens to inhabit the interior of the void. Simulations and observations both suggest that voids are not completely devoid of galaxies. They host a sparse population, often of smaller, fainter systems. Encountering one would be like finding a tiny town built far from any highway. Its stars would shine. Its gas would form modest nebulae. It would have its own satellites, perhaps. From its perspective, the universe would still include the distant walls of the void, but its local story would be written on a much smaller canvas. These rare islands of structure serve as reminders that the void is not some other kind of universe. It is the same universe, playing out the same rules, with fewer ingredients in the immediate neighborhood. Your path between them will not be a series of dramatic leaps, but an extended continuity of almost nothing happening. Long stretches of darkness punctuated by occasional, faint evidence that matter, somewhere, continues to gather and burn. If this seems uneventful, that is partly the point. The mythic language that has grown around places like the Bootes Void talks about endless falling, about disappearing into nothing, about cosmic errors and scars. The real story is quieter. It is about what happens when you simply keep going in a straight line, long enough that most of the familiar landmarks fall behind the horizon of your senses. The question that sits underneath your journey is not whether you survive, or whether the ship holds, but how motion itself should be described when the usual cues are gone. In Newton's world, falling means accelerating toward a mass. In your cabin, no such pull is felt. In relativistic cosmology, your world line is just one of many geodesics threading through curved space-time, gently bent by the combined presence of matter, and dark energy. From your own point of view, though, you are always at rest. The universe moves. The galaxies on the void's walls have peculiar velocities and participate in cosmic expansion. Their light shifts, their apparent arrangement shifts, but you are simply there, at the center of your own coordinate system, watching the pattern change. It is only when you begin to ask, very precisely, what is causing which part of that change, that the need for a more careful language about gravity and expansion appears. Is the thinning of galaxies in your sky due to you moving into a region of lower density, or due to the expansion of space stretching distances, or due to local flows in the cosmic web? What, in a universe like this, does it really mean to talk about being pushed, or pulled, or carried along? Those are not questions a window can answer. They belong to the equations that underlie the map you left behind when you first set your course for the void. To see what the universe is really doing with your path, you have to step away from the view from the cabin and look at your trajectory from the outside, in the language of gravitational fields and expanding space. From that outside vantage point, the word falling starts to misbehave. It still feels right in your mouth, but the universe no longer cooperates with what it used to mean. In the world that Isaac Newton described, falling is simple. There is some mass nearby a planet, a star, a cluster, and gravity pulls you toward it. If you drop a stone, it accelerates downward because Earth's mass is tugging on it. If you throw the stone hard enough, it curves but still comes back, unless you give it so much speed that it escapes and never returns. The direction of falling is always towards something. In that picture, empty space is mostly a background. If there is no mass near you, nothing tugs, and you just drift in a straight line forever. Motion is something you either have or do not have, and falling is what happens when an external force bends your path. Cosmology keeps some of that intuition but quietly rewires the rest. On the largest scales, the universe is not a static stage with scattered masses sitting in it. Space itself is stretching. Distances between unbound objects grow over time, not because they are flying through a fixed arena, but because the arena is expanding. That smooth expansion, what astronomers call the Hubble flow, is layered on top of the local gravitational pulls from matter, and dark energy. Your path through a void is a mixture of those influences. Part of your motion is the initial peculiar velocity you had when you left your galaxy, the individual shove that set you on course. Part of it is the general expansion of space, which increases your separation from other galaxies even if you make no further moves. Seen in co-moving coordinates, the kind cosmologists prefer, you are not plunging toward a center of anything. You are coasting while the distances around you breathe. The very idea of falling into the middle of an underdense region is, in a Newtonian sense, backwards. A void is not a mass that pulls, it is a lack of mass. The real gravitational wells live where the matter is, in the filaments and walls of galaxies surrounding the emptier cells. If you were to release a test particle near the edge of an almost spherical void and ask where it will go under the influence of gravity alone, the answer is not inward, it is outward, toward the denser structures at the boundary. A piece of classical intuition helps here, even in a modern setting. In Newton's theory, there is a result often called the shell theorem. It says that inside a perfectly symmetric shell of mass, the gravitational pulls from all parts of the shell cancel out. A test particle in the center feels no net force. Even if you move a little off-center, the forces partially cancel. The field inside is much weaker than outside. A cosmic void is not a perfect spherical shell, but it rhymes with the theorem. The mass that does exist is mostly concentrated in the surrounding walls and filaments. From your position deep inside, you feel the tug of all that material, but because it is roughly distributed in all directions, much of the net pull cancels. What remains is a very gentle gradient, pointing you, not toward the empty center, but toward wherever the nearest overdensity lies. That is why, in the language of cosmology, voids are sometimes said to evacuate. Over long timescales, matter inside them tends to drift outward, sliding down the gravitational slopes toward the walls. The interior becomes even more underdense. In plots of galaxy motions, you can see this as a flow pattern, arrows pointing from the center of a void toward its rim, tracing the slow migration of material away from the hollow. Now add the expansion of space. The Hubble flow says that, on average, the recession speed between two distant galaxies is proportional to the distance between them. But this average hides local variations. In regions where matter is dense, gravity can resist the expansion, sometimes even turn it around locally, binding things into clusters. In regions where matter is sparse, there is less resistance. The same dark energy that drives the global acceleration has less competition. The result is that voids tend to expand a little faster than the universe as a whole. Distances within them increase more quickly. Their interiors grow, and the galaxies at their edges recede from one another with a slightly greater speed than similar galaxies in more typical environments. From a distance, it looks as if the void is pushing things away. There is no new force doing that. It is the same gravity and dark energy acting on a different distribution of matter. But our language struggles to capture that without flipping to metaphors of repulsion. When the first three-dimensional maps of large-scale structure were published, some researchers wondered whether voids should be treated as special dynamical entities, bubbles in some exotic field, perhaps, or fingerprints of unusual early universe physics. Others argued that they are simply the flip side of clustering in the standard lambda CDM model, where cold dark matter and dark energy govern the overall evolution. As more data accumulated from surveys beyond the original Harvard-Smithsonian work, a consensus emerged that voids look, statistically, like what the standard model predicts. They come in a range of sizes and shapes that match simulations. They appear where you would expect them to appear if you let small initial underdensities grow over cosmic time. They nest inside one another in a hierarchy, smaller hollows inside larger basins. The discovery of the so-called Great Wall in the late 1980s reinforced this picture. When astronomers extended their redshift surveys and plotted the positions of thousands of galaxies, they saw an enormous, wall-like arrangement stretching across hundreds of millions of light-years. That wall was not a lonely structure. It was bordered on both sides by vast regions with far fewer galaxies. Together, the wall and its neighboring voids looked like part of a foam-thick ridges enclosing giant cells of thinner material. In that foam, voids are not accidents. They are fundamental components. Every wall, every filament implies, by contrast, a hollow beside it. The cosmic web could not exist as a web if matter was smeared evenly. It needs both the threads and the gaps. All of this makes the word falling more ambiguous. If you insist on using it in a cosmological context, you have to be clear about what you mean. You are not falling into a void in the way a stone falls into a well. You might say instead that you are falling out of a void, sliding away from its center toward the walls, if you let gravity and expansion decide your fate. But inside your small ship at the notional center, none of these flows announce themselves. You are in freefall, which in general relativity is precisely the state of feeling no proper acceleration. Your body is weightless. If you turn off all the engines and internal mechanisms that could push on you, you float. The only signs that anything is happening come from changes in the pattern of light on the sky. Those changes are subtle and slow. The bright galaxies that live on the walls of the void cluster into a compact region of your view, because they are all far away in more or less the same general directions. The rest of the sky is dominated by darkness and by the smooth microwave background. Over immense spans of time, the redshifts of those wall galaxies creep upward. New ones drift into or out of your observable patch, as the light from them finally reaches you or stretches beyond the sensitivity of your instruments. From your own coordinate system, you can choose to say that you are stationary and the walls are receding. That is a perfectly valid description in relativity. There is no absolute frame that everyone must agree on. Alternatively, a cosmologist drawing a diagram in co-moving coordinates might say that you have some peculiar velocity within the expanding void, and that under the influence of the surrounding gravitational potential, your world line gently bends toward a filament. Both stories describe the same geometry. One emphasizes your experience of being at rest in your own cabin. The other emphasizes your relationship to the average flow of matter in the universe. Neither story feels like the ordinary, earthbound idea of falling. The paradox is easier to feel at a smaller scale. If you float in the middle of a calm ocean with no land in sight, there is no sense of down beyond what your inner ear and the pull of Earth provide. The water around you looks almost the same in all directions. The horizon is a flat ring. You do not feel that the sea is dragging you toward any particular shore. And yet, if there are currents, if the planet is curved, if wind and tide conspire, you may slowly drift toward one coastline rather than another. The ocean does not feel like it is falling. It does not feel like it is expanding. It feels still, because your senses are too local to register the global patterns of flow. In a void, the sky is your horizon. The walls of galaxies are the distant coasts. The currents are gravity and expansion. What you feel is only isolation. What the equations see is a subtle, continuous adjustment of distances. There is another layer of strangeness hiding here. In Newtonian gravity, we often talk about forces. General relativity prefers to talk about geometry. Free fall is what it means to follow the straightest possible path in curved spacetime. Inside a void, spacetime is curved less by matter than it is in a cluster, but it is still shaped. your straightest path, your geodesic threads that shape in a way that depends on both the underdensity and the distribution of mass outside. If you draw that path on a space-time diagram, it bends gently, not toward the empty middle, but toward the ridges where matter has gathered. In other words, even in this deep underdense place, your future is still oriented by what the universe has chosen to put somewhere else. Falling, in this language, becomes not an arrow toward a specific object, but a preference for certain world lines over others, built into the fabric of the cosmos. From your perspective, this is almost impossible to feel. You can measure it. If you are patient and careful, you can send out radar pulses, track the positions and redshifts of the wall galaxies, compare them over millions of years of ship time, and reconstruct the underlying flow. You can watch the slight blue or red tilts in the microwave background caused by your motion with respect to it. All of these measurements will tell you that you are not just drifting aimlessly, you are part of a larger pattern, but at no point does the void grab you by the shoulders. It never announces, now you are entering, now you are leaving. To the physics, this is the whole point. Voids are not agents. They are the absence of agency. They are what is left in the places where gravity has chosen to work harder elsewhere. And yet, the human brain is not built to think in terms of geodesics and underdensities. It wants surfaces, edges, centers, bottoms. It wants to know whether it is rising or falling, safe or in danger. When it sees a sky that is crowded, it relaxes into a story of being held. When it sees a sky that is mostly dark, with a small knot of distant galaxies in one corner and almost nothing elsewhere, it reaches for different stories: exile, abandonment, being cast out. From the standpoint of the equations, nothing special has happened to you. Your path through space-time inside the void is only mildly different from what it would have been in a more typical region. The local laws have not changed. No new forces have appeared. The underdensity has shifted the balance between gravity and expansion, and that is all. From the standpoint of your nervous system, the situation is completely different. The loss of familiar landmarks, the stretching of timescales beyond any lifetime, the sense that the universe has thinned out in every direction, those things add up to an experience for which your inner vocabulary is almost empty. This mismatch between what the universe is doing and what your brain can name is where the true strangeness of falling into almost nothing lives. The void does not bend your body in any unusual way. It bends your sense of context. It erases the usual cues that tell you where you belong. The physics can say, quite calmly, that voids are just underdense regions where the standard cosmological model plays out in a slightly different key. The mind, placed there even in thought, hears a different music. It hears the volume of the universe turned down, the presence of others reduced to a distant murmur, and in that quiet, a new kind of question starts to form, not about forces or flows, but about what happens to a sense of self when the structures around it recede beyond sight. When the structures around you thin out, the first thing that really changes is not the physics. It is the sky. From the center of a supervoid, the night is not a perfect black screen. It just refuses to behave like any night you have ever known. There is no Milky Way cutting across the darkness as a dense, milky river. No thick band of unresolved stars. No arch of light hinting that you are wrapped inside a spiral disk. Instead, most of the dome above you is bare. Not empty in the strict sense, but visually quiet. Here and there, scattered across the black, are a few pale smudges, distant galaxies and clusters, sitting on the far walls of the void, like islands seen from the middle of an ocean. Those islands do not fill the sky, because almost all the bright matter lives in the filaments and sheets that surround the underdense basin. Most of the visible light reaching you comes from roughly the same directions. If you could mark every photon that originated in a galaxy and trace its path, you would find that they arrive from a small family of patches on the sphere around you. Not from everywhere. Your eye, which evolved under a sky where stars are generously sprinkled, would find this lopsidedness hard to accept. Look long enough, and you might start to recognize that the little foggy knots in one corner of your view are not stars at all, but entire clusters of galaxies stacked along the line of sight. Some will have the stretched, elongated look that comes from being slightly smeared by gravitational lensing and distance. Some will be barely brighter than the background glow of your instruments. Between them, stretches of sky will hold nothing your retina can register. And yet, if you could tune your senses differently, you would discover that every direction around you is filled with light. It is just not light in the narrow band that human eyes have access to. At microwave wavelengths, the sky from a void is as full as the sky from a galaxy. The cosmic microwave background wraps you in a nearly uniform bath of photons, each one with an energy corresponding to a temperature of roughly 2.7 Kelvin. That number means little to instinct, but in physical terms, it is a measure of how much the early fireball has cooled as space has expanded. From your point inside the void, those microwaves arrive from all directions with almost the same intensity. The uniformity is not perfect. There are tiny fluctuations in that background, little hot and cold patches that map the seeds of structure in the early universe and the later influence of evolving gravitational wells and hills. When Arno Penzias and Robert Wilson first heard the hiss of this radiation with their horn antenna in the early 1960s, they had no idea they were listening to relic light from a time when no galaxies yet existed. They were bothered by an unwanted noise. Only later did theory and observation come together to reveal that the noise was, in a sense, the oldest story the universe can tell. Sitting in your craft at the center of an underdensity, the microwaves that wash over you have traveled for more than 13 billion years since that hot, dense phase. They have crossed countless filaments and voids. The underdense region you currently occupy will leave only a very small imprint on their pattern, through the way its shallow gravitational potential evolves as dark energy pushes the universe into accelerated expansion. That subtle effect, folded along the paths of many photons, is one of the reasons cosmologists look at the microwave background so carefully. It carries information not only about the early universe, but also about how structure, including voids, grew later on. In the early years of this century, one patch of that background drew extra attention. Maps from a satellite called the Wilkinson Microwave Anisotropy Probe showed a region in the southern hemisphere of the sky that was unusually cold, larger and deeper than typical hot or cold spots. Later, the Planck mission confirmed it. The feature became known simply as the cold spot. Among several possible explanations, one idea was that photons passing through an enormous underdensity, a supervoid, might lose a little extra energy because of the way the void's gravitational potential changed while they were in transit. In that picture, a region of space that is relatively empty could cast a kind of subtle thermal shadow on the oldest light in the universe. Follow that line of thought far enough, and you arrive at a strange conclusion. Even the most rarefied regions, the places where galaxies are scarce and matter has mostly flowed away, can still leave fingerprints on the cosmic background that fills your sky. The void is not simply where the universe fails to appear, it is one of the actors that quietly shapes the pattern of what you see. None of this is obvious to your bare senses. To them, the dominant fact of the sky is distance. The walls of the void are so far away that every photon from a galaxy there has been in flight for hundreds of millions of years. By the time it lands in your detector or on your retina, the Earth it left toward the Earth whose astronomers you once were may no longer resemble the one you remember. Think of a single photon that began its journey when the continents on our planet were in different places, when mountain ranges had not yet lifted into their current forms, when the Pacific Ocean had another outline. That photon leaves the outskirts of a galaxy on the void's boundary and spends an almost inconceivable time in transit, crossing the underdense basin at the finite, unchanging speed of light. Only then does it brush the sensor on your little ship, appearing as a tiny contribution to a faint, distant smear. Every speck of visible light in your sky has a history like that. Each is a messenger from a different geological chapter of the worlds that might exist on those galaxies' planets. The glow on your dome is not a snapshot. It is a mosaic of old news. On human timescales, though, that news barely changes. If you could somehow live inside your craft for 1,000,000 years, checking the sky at the beginning and the end of that span, you would find that the arrangement of those smudges has shifted by only the smallest amount. Redshifts would be microscopically higher. Angular sizes would have shrunk a little as expansion increased the distances. A few faint galaxies might have dropped below your detection threshold. Others might have brightened, but the general impression would be the same, a cluster of weak lights in one part of the sky, surrounded by a vast, almost indifferent dark. This slow evolution contrasts sharply with the kind of space we are used to seeing in films. In a movie like Gravity, released in the year 2013, The void between orbiting stations is dramatic but visibly connected to Earth. The planet fills half the frame. The sun floods every shot with glare and shadow. Debris races past. Even in the most desolate wide shot, there is always a nearby world to anchor the eye. In a real cosmic void, that anchor is gone. There is no looming globe, no sun large enough to cast a local geometry of light and dark. Whatever star your craft left behind is now a point among points, easy to lose track of. The nearest galaxies are far too distant to resolve into disks without strong magnification. If you turn off your instruments and look with unaided eyes, the sky feels more like a minimalist painting than a panorama, a handful of strokes on a very large canvas. The absence of a foreground does something subtle to your sense of scale. On Earth, the horizon, clouds, and the silhouettes of mountains all conspire to give distance a shape. Even in low Earth orbit, the curvature of the planet and the wash of sunlight off the atmosphere tell you roughly how far you are from the surface. In the void, where there is no nearby structure, distance loses that layered feel. Everything bright collapses onto the same distant shell, near and far blur together. You can reconstruct the depth with spectroscopy and careful measurement. You can calculate which galaxies are a little closer, which are far beyond them. You can build your own private survey, redoing in miniature what the Sloan Digital Sky Survey did on a grander scale, measuring redshifts, turning colors and lines into distances, drawing a three-dimensional map from the two-dimensional sky. But the raw sensory impression does not carry that richness. It is a flat scatter on black. There is, in this, a kind of reversal of our usual experience. On a clear night on Earth, even without instruments, you can feel that the Milky Way is not a flat decoration. Its thickness, its texture, the way some regions are rich with clusters while others are veiled by dust, all of these cues hint that you are inside something with depth. The night invites you to picture a disk, a bulge, a halo. From the heart of a supervoid, the sky does the opposite. It hides the three-dimensional structure in simplicity. It offers you so little to work with that any sense of belonging to a larger architecture has to be constructed intellectually, not felt. Time, too, changes its character. In ordinary life, time is bound to cycles, days, seasons, orbits. The movement of the sun and moon, the slow precession of familiar constellations. In a galaxy, there are still cycles on human scales, the orbits of stars in clusters, the variability of certain luminous objects, the occasional flare of a supernova. There is a sense, however faint, that if you wait long enough, the sky will reward your patience with drama. In the void, drama moves to a different register. The time scale on which the sky truly changes is measured not in years or centuries, but in hundreds of millions of years. Entire civilizations could rise and disappear on a planet in one of those distant galaxies, while their host cluster, seen from your vantage point, barely shifts a fraction of a degree. The living time of any observer like you is a flicker laid on top of a backdrop that hardly stirs. You could, of course, create your own markers. You could count the faint increase in the average redshift of the wall galaxies as the universe expands. You could track the tiny drift in the temperature of the microwave background as dark energy pushes the cosmos into a more dilute state. These would be real changes, measurable and meaningful to a cosmologist. But they would not feel like the ticking of a clock. They would feel like the slow, almost imperceptible cooling of a vast room. The contrast with home reshapes itself in words. On Earth, we say we are under the sky. In a galaxy, we might say we are within it. From a void, the grammar blurs. There is sky, but it is not above you in any meaningful sense. You are not under or within anything dense. You are suspended in a region where the universe has chosen to speak softly. And yet, that softness hides an odd fact. In terms of information content, you may be one of the most complex patterns in hundreds of millions of light years. Your body, your nervous system, the ship that keeps you alive, all of them are intricate arrangements of matter and energy held far from equilibrium. Compared to the thin gas and faint galaxies around you, you are dense with structure. The sky may be nearly empty of detail, but you are not. What does it do to a mind to look up at a dome that offers so little, and realize that most of the pattern in this part of the universe is currently folded into your own thoughts. How does a sense of place form when your horizon contains almost nothing to lean on? Those are not astrophysical questions. They do not live in equations or surveys. They live in whatever happens inside a brain that is trying to update its picture of where it exists. If the sky is our first mirror, then avoid sky as a mirror that reflects back something unsettling, almost no context, almost no neighbors, only a distant web and the quiet murmur of ancient light. To follow that thread, we have to shift, once more, from maps and spectra to the more fragile terrain of perception, to what happens when a body built for crowded horizons finds itself, even in thought, in a place where the universe has thinned to the point of abstraction. When people first tried to study what happens to a human mind when the world goes quiet, they did not need a spaceship or a cosmic void. A dark tank of warm water was enough. In the middle of the 20th century, researchers began asking volunteers to lie in sensory deprivation tanks, enclosed chambers filled with body temperature, salt water, sound deadened, lights out. No sight. Almost no touch beyond the uniform pressure of water, no changes in temperature or smell. After a short time, many people reported a kind of drifting calm. Stay longer, and the calm began to fracture. The brain, starved of input, started to supply its own. Flecks of light that were not there, echoes of voices, a slipping sense of where the body ended and the surrounding water began. Nothing violent had happened. No one had been harmed. The laws of physics inside the tank were exactly the same as outside. The only difference was that almost all the usual signals had been turned down. That was enough to make the mind lose its grip on what it normally calls real. The void is not a tank, but in one sense it is an even more severe experiment. It does not take away all sensory input. Your ship still hums, your body still aches, your instruments still show numbers, yet it strips away almost everything that tells you where you are in the universe. No rising sun, no familiar constellations swinging around a pole, no galactic plane arching overhead, only a handful of distant galaxies, fixed in place for longer than any lifetime, like a wall painting that never changes. Researchers who plan for long-duration spaceflight already worry about something much milder than this. During the Mars 500 project in the early years of the 21st century, volunteers were sealed in a simulated spacecraft for more than a year, following a schedule that mimicked a crude journey to Mars and back. There was artificial day and night, regular communication with the outside world, work to do. Even so, monotony and confinement took a toll. Mood dipped, sleep patterns shifted, small interpersonal tensions grew large. In Antarctic research stations, crews who winter over report a similar thinning of experience. Months of darkness, the same walls, the same handful of human faces, the same wind outside. The world does not vanish, but its variations shrink. Psychologists call it sensory monotony. The brain, deprived not of all stimuli but of change, responds with fatigue, anxiety, sometimes a numbness that is indistinguishable from despair. Our imagined traveler in a supervoid faces something deeper than monotony. The cabin may be filled with all the small noises and textures of daily life, but the universe beyond the hull has been reduced to a static pattern. You can look up at the same smudge of galaxies in the same corner of the sky for a century and it will be, to your eyes, the same. You can wait for the cosmic equivalent of sunrise, and it will not come. We often say that we know who we are because of what we stand next to. City dwellers define themselves against the noise and light of streets. People in rural places define themselves against open fields and long distances. We are used to being, in some way, the contrast between our inner life and the outer scene. In a void, that contrast is eroded. The outer scene flattens toward almost nothing. It stops offering back any rich pattern for the mind to push against. What remains is a simple equation: this body, these thoughts, these memories, and then, for hundreds of millions of light years in all directions, almost no structure at all. If you stand in the cabin and look down at your own hands, the imbalance becomes startling. Under your skin, cells churn. Neurons fire in intricate webs of activity. Blood flows through capillaries whose total length, if stretched out, would dwarf the dimensions of your ship. You carry in your skull a network so complex that we still cannot fully chart it. even with all our techniques. Compare that, even roughly, to the space around you. Within a volume of hundreds of millions of light years, the total amount of organized structure, stars, planets, dust clouds, fields, is modest. Thin gas, a trickle of dark matter currents, a few faint galaxies at the edges. If you could somehow measure the total information content inside that sphere, the number of distinct, meaningful patterns, your own nervous system would be a non-trivial contribution. You are, quite literally, a knot of higher complexity drifting in a place where complexity has mostly failed to appear. Loneliness, in ordinary language, is about other people. It is about the absence of voices, of touch, of shared routines. The void introduces another kind of absence. It is the lack of any obvious larger structure to belong to. On Earth, you belong, whether you think about it or not, to continents, to a biosphere, to a planet orbiting a star inside a galaxy that has neighbors. Even if you feel cut off socially, you are still embedded physically. In your void cabin, that embedding feels fragile. The Milky Way is a point. The local group of galaxies is a slightly richer knot inside a distant haze. The cluster that contains them is a faint freckle on the wall of the void. None of these things curve over you as an arch. None fill the sky as a container. The sense of being inside something larger is replaced by the sense of simply hanging. The mind does not have ready-made stories for that. It can borrow metaphors, castaway, exile, cast out of the garden of stars, but those are imports from smaller worlds. They do not quite fit the scale. Your situation is not that you have been pushed away from the center, it is that there is no center to push away from. The universe, even in its busiest regions, is mostly empty. The void has only made that fact explicit. Experiments with sensory deprivation tanks showed that when the world becomes uniform, the brain begins to invent detail. In a cosmic void, something parallel might happen. A person might begin to project significance onto the few galaxies that remain visible. Those would become, in imagination if not in fact, special, the only neighbors, the only possible witnesses. Stories might form around them, names, imagined histories, roles they play simply by virtue of being there. Or perhaps the opposite would occur. Instead of elaborating, the mind could start to flatten. If nothing in the external scene answers your attempts to impose narrative, if the view remains stubbornly sparse, no matter how long you wait, a kind of resignation might set in. The sky would cease to be a stage and become, instead, a reminder that most of reality never asked you to be part of it. There is a philosophical current that says existence is relation, that a thing is what it is only through its connections to other things. Physics, at least in its mainstream form, is more minimal. It is content to say that a configuration of fields and particles exists, even if no one observes it, and even if it has very few interactions. A lone electron in an otherwise empty universe is still a valid solution to some equations. Human experience sits uncomfortably between these two views. Your body and brain are, in a strict physical sense, a configuration of matter and energy that would exist even if no one ever named it. At the same time, your sense of being a self depends on a mesh of relations to other people, to places, to routines, to a remembered past and an anticipated future. Strip those relations away, and what remains may still be a perfectly valid physical system, but it does not feel like a life. The void forces that gap open. It says, from the point of view of cosmology, nothing much has changed. You are still in the universe, still subject to the same laws, still part of the same large-scale structure, just located in a region where the density is low. From the point of view of a mind built on contrast and relation, everything has changed. The mirrors that normally reflect your existence back to you, other faces, busy skies, the hum of a planet, have been moved beyond sight. If you stay there long enough, the question that began as science fiction folklore, what would happen if you fell into the biggest void, dissolves into a quieter one? What does it mean to continue existing when the universe around you has become almost silent? When there is nothing near to answer back? Does the word near still have meaning? Does the word belonging? Physics does not answer those questions. It does not need to. For cosmology, voids are features of the density field, underdense regions that play a role in how matter clusters and light travels. They are part of the machinery by which the universe builds whatever structure it does have. They are not concerned with how it feels to sit at their centers. To understand that machinery, though, you have to return to the maps, to the simulations where dark matter flows along filaments and drains the basins between them, to the surveys where the positions of thousands of galaxies sketch the outlines of a web, the same void that looks, from inside, like an absence of context, looks, from outside, like one cell in a vast foam. It is not an afterthought. It is an essential gap, the negative space that makes the cosmic pattern possible. Seen from that larger vantage point, the lonely cabin in the supervoid is no longer the whole story. It is a small complication in a much wider process, the way nothing in particular, over billions of years, helps carve out the places where something in particular can form. From far enough away, the cabin in the void shrinks into a point, and what takes over is the pattern that made both the cabin and the void possible in the first place. The story stops being about one traveler and becomes a story about how the universe chose to draw itself. Those first wedge-shaped maps from the Harvard-Smithsonian survey were like rough sketches of that drawing. A thin slice of sky, a scatter of points, enough to hint that galaxies preferred to line up along arcs and clusters and left great hollows between. As more surveys followed, with better instruments and wider coverage, the sketch thickened into something more like a woven fabric. Superclusters of galaxies appeared as nodes. Filaments connected them. Dark gaps separated the strands. People began to use a phrase that has stuck ever since the cosmic web. One way to see that web is historical. Start with the tiny ripples in density seen in the cosmic microwave background, the faint mottling that satellites like Wilkinson Microwave Anisotropy Probe and Planck turned into detailed maps. Those ripples are slight differences, one region a little denser than average, another a little less. Let gravity act for billions of years on that unevenness, and the slightly denser places begin to pull harder. Matter drifts toward them. The slightly emptier places lose still more matter to their neighbors. Over time, the contrast grows. Peaks grow higher. Basins deepen. Filaments form where flows converge. Voids open where flows diverge. In numerical experiments, cosmologists give this process a kind of artificial life. They set up a cube of virtual space, fill it with particles representing dark matter, and nudge the initial positions and velocities so they match what the microwave background suggests. Then they let the system evolve under gravity and cosmic expansion. The particles fall, merge, stream, clumps, form, stretch into filaments, gather into knots. Between these structures, great low-density cavities swell. When they stop the simulation and take a cross-section, the picture is startlingly similar to the real maps from galaxy redshift surveys, a sponge-like arrangement where overdense structures form the spongy skeleton and voids are the holes. The agreement is not perfect in every detail. That is where ongoing work lives, in those mismatches. But at the level of broad pattern, the universe we see appears to be the one we would expect from such an origin. The discovery of enormous walls of galaxies helped fix this image in place. In the late 1980s, when astronomers extended their redshift surveys to cover more of the northern sky, they found a structure now called the Great Wall, a colossal aggregation of galaxies stretching across hundreds of millions of light-years like a ridge of clustered matter. That wall did not stand by itself in an otherwise uniform cosmos. It was wrapped by voids on either side, vast underdensities that highlighted its presence by sheer contrast. Once you know to look, you find similar patterns elsewhere, other walls, other extended filaments, each with corresponding cavities. The foam analogy becomes hard to escape. The universe is not a fog. It is closer to a loaf of bread in which the crumb and crust trace where matter has settled and the air pockets trace where it has not. New eyes in space have only strengthened this impression. On July 12, 2022, the James Webb Space Telescope team released one of its first deep-field images, a seemingly tiny patch of sky held for many hours in the telescope's gaze, revealed to contain thousands of galaxies, some so distant that their light left when the universe was still very young. The initial reaction focused on abundance, on how many objects were crammed into that small rectangle. But when astronomers take such deep images and add distance information, building three-dimensional reconstructions from redshifts and colors, the abundance resolves once more into pattern. Galaxies in the deep field are not sprinkled evenly along every line of sight. They cluster into groups and filaments. There are regions where their number densities spike, and regions where they thin. Even within that apparently packed square of sky, the universe is acting out the same preference structure and gap. What changes with each new survey and simulation is not so much the basic picture as its resolution. Early maps showed only the coarsest threads in the web, like a blurry photograph. Later projects, such as the Sloan Digital Sky Survey and other wide-field campaigns, sharpened the view, revealing smaller filaments and subvoids nested within larger ones. At each stage, voids are not erased by greater data. They proliferate. Big ones contain smaller ones, like hollows within hollows. It is easy, from a human point of view, to treat the gaps as afterthoughts. We like to name and count the things that glow. Clusters get catalogues. Filaments get traced and colored. Great superclusters are given mythological names. Voids, by contrast, are often defined negatively as regions where the density falls below some threshold. They are where the objects we pay attention to are not. That bias can seep into language. Articles call voids anomalies, holes, defects. Stories talk about regions the universe forgot to fill. Yet in the dynamics of large-scale structure, there is nothing accidental or forgotten about them. Voids are as inevitable as the filaments they frame. Without them, the web could not have the form it does. A more elastic metaphor may help. Think of a piece of music. The notes get all the explicit symbols on the page. They are what we hum and remember. But the rests, the silences between phrases, are what give those notes shape. Remove every pause, fill every gap with sound, and the piece collapses into noise. The emptiness is not an error in the composition. It is part of the grammar. Voids play a similar role. They are the cosmic rests, the intervals where matter has not spoken. Their very lack of structure is what makes the structures elsewhere stand out. The bright clumps of galaxies at the nodes of the web look like clumps only because they are surrounded by volumes that are relatively bare. In the language of statistics, voids help determine the spectrum of density fluctuations, the way matter is spread out across scales. They affect how light from the microwave background is lensed and shifted. They influence the paths along which gas can flow into galaxies, feeding star formation. They are not quiescent bystanders. They participate in the way the universe evolves. Seen this way, the thought experiment of a lone ship drifting through the center of a supervoid takes on a different tone. From inside, the traveler experiences a lack of context, a sense that they are far from anywhere that matters. From outside, in the coordinates of cosmology, their path takes them through one of the fundamental elements of the cosmic architecture. They are not in a place the universe ignored. They are in one of the negative spaces that make the positive spaces possible. There is a quiet irony here. People often carry a private sense of being the exception, of standing somehow at a slight angle to the rest of the world. Not quite fitting the pattern, not quite part of the main cluster. That feeling can be painful. It can also be, in some moods, a source of identity, the outsider who stands at the edge and watches. A galaxy parked just off the main wall of a void might, in a fanciful mood, claim the same. It sits near a vast underdensity, looking out across hundreds of millions of light-years of thinly populated space, while the denser filaments bustle elsewhere. It is not at the center of its cluster. It is not in the thick of any supercluster crossing. It lives at an angle to the busiest intersections of matter. From the standpoint of physics, that galaxy is nothing special. It follows the same rules, draws from the same reservoir of gas, turns matter into stars in the same broad way as any other. From the standpoint of its local environment, though, it occupies a kind of threshold. It marks one boundary between where the universe has chosen to gather itself and where it has mostly chosen not to. The human tendency to feel like an exception may share a distant kinship with this arrangement. Consciousness gathers in small, dense knots of biological structure, surrounded by vast volumes of matter and energy that never become aware of themselves at all. A mind is a local complication, a small violation of the average, floating in a medium that is overwhelmingly indifferent. It would almost be surprising if such a thing did not sometimes feel out of place. The cosmic web, with its filaments and voids, gives that sensation a literal backdrop. It shows that on the largest scales, being in the thick of things, or at the edge of things, is a matter of position in a pattern that no one designed and that almost everything in the universe never thinks about. Your ship in the void is not a punishment. It is a coordinate choice. To understand what that choice implies and what kinds of questions it tempts us to ask, we have to look more closely at the oddities that still puzzle cosmologists, places where voids, cold spots, and statistical flukes intersect. Those are the regions where the neat picture of the standard model begins to wobble, and where our desire to find meaning in the gaps runs up against the stubbornness of data. Some parts of that web still refuse to sit quietly inside our equations. They sit there like knots in the tapestry, daring us to decide whether they are accidents or hints. One of those knots is drawn not in galaxies, but in temperature. When the first full sky maps of the cosmic microwave background from the Wilkinson Microwave Anisotropy Probe were released in the early years of this century, cosmologists did what they always do. They subtracted known effect, smoothed the data, and looked for patterns. Most of what they saw matched expectations from the standard picture of a nearly uniform early universe, with tiny fluctuations that later grew into structure. But in the direction of the constellation Eridanus, there was a patch that seemed too large and too cold for comfort. This microwave cold spot covers a few degrees on the sky and is tens of microkelvin cooler than the average background. In a map where typical fluctuations are only on the order of a few tens of microkelvin across angular scales of about 1 degree. It is not that there are no other hot or cold regions. The microwave sky is full of them. What makes this one special is its combination of size and depth. In simulations of a universe like ours, such a feature is statistically unlikely, though not impossible. Depending on the exact analysis, the odds of getting something similar purely by chance hover at the level where people start to raise their eyebrows but hesitate to call it a discovery. Because the cold spot shows up in microwave light, not in galaxy surveys, its origin is not immediately obvious. One family of explanations stays conservative. Perhaps it is simply a rare fluctuation in the primordial plasma, a patch of slightly lower temperature imprinted at the time when the cosmic background was released. Another family reaches for new physics. Maybe this region carries the imprint of a cosmic texture, a kind of topological defect in a field that formed when symmetries broke in the very early universe. Texture models have been developed that can reproduce something like the cold spot's profile, and Bayesian comparisons have been made between that idea and others, though none has yet closed the case. A third line of thought looks not to the early universe, but to its later scaffolding. If, between us and the surface of last scattering, there lies a very large, underdense region, a supervoid, then photons passing through that region will feel the changing gravitational potential along their paths. Because dark energy causes the expansion of the universe to accelerate, the depth of a void's gravitational well, or rather hill, can change while light is in transit. The integrated Sachs-Wolfe effect describes how this evolution can leave a net energy shift on the photons. In simple terms, crossing an evolving void can make background photons emerge slightly cooler than they would otherwise have been, creating a cold patch on the microwave map. This suggestion motivated astronomers to look carefully along the line of sight toward the microwave cold spot, using galaxy surveys to see whether the large-scale structure in that direction looks unusual. Over the past 2 decades, evidence has accumulated for a genuine supervoid in Eridanus, an extended underdensity in the distribution of galaxies, now often called the Eridanus supervoid. Analyses of near-infrared and optical catalogs have found that this region contains fewer galaxies than typical patches of the same size, and that it appears as a significant trough in reconstructed dark matter maps based on gravitational lensing. At first glance, that seems promising. A cold feature in the microwave background and a large underdensity in the nearby universe lined up along the same direction invite a causal link. Indeed, detailed modeling within the standard lambda-CDM cosmology suggests that the Eridanus supervoid can contribute some of the observed temperature decrement through the integrated Sachs-Wolfe effect. But when researchers estimate just how much of the cold spot's depth the void can account for, the answer is modest: a fraction, not the whole. Under reasonable assumptions, the void appears able to explain perhaps 1/10 or 1/5 of the anomaly. The rest would still have to come from either a primordial fluctuation or something more exotic. Later work has complicated the picture further. Some teams have argued that when one takes into account the full statistics of voids and the uncertainties in the data, the supervoid explanation struggles to be the main cause of the cold spot. Others have emphasized that, while the void alone may not suffice, its presence still strengthens the case that large underdensities can leave measurable imprints on the microwave background, and that the cold spot remains a valuable laboratory for testing how well Lambda CDM really describes such coupled phenomena. There are even recent analyses that conclude, cautiously, that the supervoid hypothesis as a sole explanation is disfavored, keeping the possibility open that the cold spot is either an extreme statistical fluke or a window onto new physics. Outside the technical literature, the cold spot has led a more dramatic life. Popular articles and documentaries have not resisted giving it nicknames: the Great Void, the Cosmic Bruise, even the fingerprint of another universe. Some pieces have speculated about quantum entanglement with a parallel cosmos or collisions between bubble universes in an inflationary multiverse, ideas that are intriguing to theorists but rest on layers of assumption far beyond what the data alone demand. The same pattern appears with the Bootes void and other extreme underdensities. Headlines frame them as holes in reality, glitches, scars. The underlying papers, written in the cautious language of statistics and model comparison, rarely go that far. For working cosmologists, anomalies like the cold spot occupy an ambiguous space. On the one hand, the standard Lambda CDM model has had remarkable success in explaining a wide range of observations, the overall spectrum of fluctuations in the cosmic microwave background, the distribution of galaxies on large scales, the way clusters grow, the relative abundances of light elements. In that context, a handful of low-significance oddities are expected. In any rich dataset, some region or feature will look surprising simply by chance. On the other hand, history is full of small mismatches that later turned out to be clues. The precession of Mercury's orbit, the ultraviolet catastrophe, the mismatch between nuclear decay rates and classical expectations. Each began as a nuisance, something that did not quite fit. Each eventually forced a change in the framework. The cold spot sits under that same ambiguous light, perhaps a random high-sigma fluctuation, perhaps the first hint that something in our picture of the early universe or of dark energy's role is incomplete. Either way, voids are in the story. Whether or not the Eridanus supervoid explains most of the microwave anomaly, it is undeniably present along that line of sight and undeniably unusual in scale. It is one of the largest known underdensities in the cosmic web, and its relation to the background behind it is now being probed with ever better data from surveys like the Dark Energy Survey and future projects. For the traveler we have been following in thought, none of this changes the view from the cabin. If the void beneath the cold spot turns out to be slightly larger or smaller than first thought, if its contribution to the microwave temperature is revised up or down, the sky from its center remains what Chapter 6 already described, a cluster of faint galaxy smears in one part of the dome, a smooth microwave glow everywhere, and long stretches of darkness in between. The physics of their free fall does not care whether cosmologists classify the region as anomalous or typical. The equations of motion are indifferent to whether a particular temperature decrement is a 1 in 50 or a 1 in 500 fluctuation. What does change, quietly, is the way we tell ourselves the story of such places. If a void aligned with a cold spot were definitively traced to some exotic relic of the early universe, a collapsing texture, a scar left by a collision with another inflationary bubble, then the narrative temptation would be strong. The emptiness would become a signpost, a place where the universe once did something exceptional. People would point to that patch of sky and say, "Here." The rules bent. If, instead, the cold spot slowly settles into the category of rare but ordinary fluctuations within Lambda CDM, and the supervoid along its line of sight is understood as an extreme but still natural member of the void population, then the story is different. The underdensity becomes, in a way, just another part of the foam, not a wound, not a message, but a slightly more dramatic version of what the universe does everywhere, leave most of its volume thinly populated. Between these two extremes lies a spectrum of possibilities, and current data have not yet pinned the cold spot to any one of them. The debate continues in papers and conferences, refining models, sharpening statistics, looking for new observables. It is a useful tension. Anomalies push theory and observation to be more precise. They force us to test our assumptions. Underneath that scientific work, though, is another question that does not appear in abstracts. Why are we so eager for the voids to be special? Why do headlines so readily leap from large underdensity to tear in the universe or evidence of another cosmos? Perhaps part of the answer is simple. Extraordinary stories are easier to tear, remember. But there may be something else. Accepting that even the most dramatic emptiness is just another normal outcome of known physics means accepting that the universe's vast regions of almost nothing are not mistakes. They are the rule. That is a harder thought than it first appears. It suggests that the background state of reality is not fullness, but near emptiness. And that all the things we care about, stars, planets, lives, histories, are thin decorations on that base. Calling a void a portal or a scar makes it feel less mundane, more like a secret door in the architecture. Calling it typical leaves us face to face with a quieter, perhaps more unsettling idea that nothing much happening is, on the largest scales, exactly what the universe mostly does. From the perspective of our lone ship, drifting in a supervoid, this distinction is abstract. Whether the underdensity outside the window is an ordinary member of a statistical distribution or the rare signature of some early universe drama, the experience of being there does not change. The same distant walls of galaxies, the same sparse sky, the same sense that usual categories of near and far, crowded and empty, have been stretched beyond familiarity. What shifts is where we think meaning lives. Are we tempted to assign significance to the place itself, to make the void into a stage for hidden events? Or are we willing to let the place be ordinary and instead look back at the small, improbable structure inside the cabin, the body and mind asking the question as the thing that is, in a statistical sense, strange? That is the direction in which the final step of this journey leads. Not toward an answer about what the cold spot finally is, but toward a quieter reckoning with what it really means to say you have fallen into a cosmic void not as a victim of a glitch, but as one more delicate pattern floating through a universe where almost all the volume belongs to almost nothing. The delicate pattern, floating through almost nothing, turns out not to be the void at all. It is you. The rumor that started this journey was simple and a little theatrical fall into the biggest void in the universe, and you will fall forever, lost in nothing until the universe goes dark. It is the kind of sentence that spreads easily. It feels like a punishment wrapped in cosmology, as if the universe had trapdoors. But after walking through the maps and the equations, after tracing the history from horn antennas to deep fields, the rumor shrinks. A void is not nothing. It is a region with less of some things and more of others. Less matter, less starlight, less local structure. More expansion, more background, more silence. You do not vanish when you move into such a place. You just run out of nearby company. In that sense, the thought experiment has been hiding its subject. We pretended to talk about where you were going. The real question was always about what was going with you. Take the cabin again, drifting near the center of a supervoid. Around it, for hundreds of millions of light years, there may be nothing as intricate as the object sitting on the chair inside. Your body is a temporary knot of low entropy. A local pocket of order in a universe where the usual direction of time is toward more disorder, more mixing, more spread. Cells maintain gradients. Neurons maintain potentials. Molecules are arranged in patterns that would be incredibly unlikely if you shuffled them at random. That is not flattery. It is bookkeeping. If you compare the microscopic configurations available to a cloud of thin gas in the void with the configurations available to the network inside your skull, the difference is stark. The gas does not remember. Your brain does. It tracks sequences, builds models, writes and rewrites stories. It is an unlikely arrangement that appears, runs for a while, and then dissolves back into more ordinary states. From that perspective, the image of you as a victim of the void, a small thing hurled into emptiness, flips. The void is the background. You are the anomaly. You are the improbable structure that the universe has allowed to crystallize on one small rock, orbiting one star on one filament of the web. When you drift into an underdense region, the universe has not singled you out for erasure. It has simply allowed one of its rare, highly structured patterns to pass through a region where it built very few others. The history that led us here is, itself, a record of expectations being quietly dismantled. In the mid-1960s, two engineers at Bell Labs, Arno Penzias and Robert Wilson, tried to get rid of a hiss in their radio antenna. They climbed into the horn, scraped out pigeon droppings, adjusted electronics. The noise persisted. Only later did it become clear that what they called interference was the faint glow of the cosmic microwave background. Light released when the universe was young and dense, now cooled and stretched by expansion. The sky, which had seemed dark between the stars, turned out to be filled with ancient radiation. A couple of decades later, in the early 1980s, astronomers plotting galaxy redshifts saw something else the eye alone had missed. Instead of a uniform fog of galaxies extending in every direction, their three-dimensional maps showed filaments and walls, with enormous voids between them. Space, which posters and planetarium domes had taught us to imagine as a crowded sea of stars, turned out to be more like foam-thin, luminous surfaces draped over deep hollows. By the late 1980s, with the discovery of structures like the Great Wall, the scale of that foam had become impossible to ignore. By the early years of this century, satellites like Wilkinson Microwave Anisotropy Probe and Planck had mapped the tiny fluctuations in the microwave background with exquisite precision, and surveys like the Sloan Digital Sky Survey had filled in vast swathes of the web. Then, in July of the year 2022, the James Webb Space Telescope released deep field images in which every patch of black resolved into thousands of galaxies, some from a time when the first structures were only beginning to form. Each step widened the frame. Each step made the universe less like the intuitive picture. A static dome became an evolving space. A smooth backdrop became a patterned web. A quiet darkness between stars became a haze of ancient light and the faint pull of dark matter. Through all of that, one idea kept being revised: what it means to be small. At first, smallness meant being a speck among many specks. A person is tiny compared to a planet tiny compared to a star tiny compared to a galaxy tiny compared to the observable universe. Smallness meant being outnumbered, dwarfed by the sheer count of other things. Void cosmology offers another flavor of the same feeling. On the largest scales, matter is sparse. The Milky Way and its neighbors occupy a thin strand between much larger underdensities. Our local group of galaxies is separated by millions of light-years from the next cluster. Even in relatively dense regions, the average distance between large galaxies is vast compared to their own sizes. The universe is not a packed crowd. It is a mostly empty hall with a few people scattered across it. So you are small in two ways at once. Small in size compared to the web as a whole, and small in abundance compared to the emptiness that fills almost all of it. But those two smallnesses point in different directions. One invites you to feel crushed by how much else there is. The other invites you to notice how little there is, and how much is happening inside the few places where matter has complicated itself. The cabin in the void sharpens that second invitation. It shows that even if you remove the galaxy, the neighborhood, the obvious context, the basic situation does not change. You are still a local spike in complexity, floating in a medium that is, by comparison, simple. You are still a bundle of low-entropy processes in a universe whose default is to spread energy thin. That insight is not about importance. The universe does not attach value to any of this. It does not prefer the structured knot to the thin gas around it. It simply allows both, as consequences of the same initial conditions and the same laws. But from the inside, from the point of view of a mind that only knows what it knows because structure has been maintained in its tissues, the contrast is hard to ignore. Bring the camera back now from the hypothetical cabin and place it where you actually are, on a small planet, in orbit around a star, part of a spiral arm in the Milky Way. It feels, on most days, like the opposite of a void. Traffic, weather, messages, screens, voices. The density of events in human time is so high that it can be hard to imagine that beyond the thin layer of atmosphere and magnetosphere, the cosmic situation is not that different from the one we just imagined. But it is. The Earth itself sits in the depths of intergalactic space. Beyond the warm shell of the solar system, distances to the nearest stars are measured in light-years. Beyond the cluster of nearby stars, The gaps between spiral arms are vast. The Milky Way, when placed in the web, is a local overdensity surrounded by volumes where there is almost nothing. Our entire visible history, every story, every conflict, every quiet evening, has unfolded on a small island of matter, in a local pocket of the same near emptiness that defines voids. In that sense, you are already in the thought experiment. You do not need to travel to Boötes or Eridanus. You are suspended, at this moment, in a region of space from which all other large galaxies are separated by millions of light years. The universe does not look like that when you stand in a city at night, or when you watch a film shot from orbit. But on the scales that matter to cosmology, this is a void-like environment. Space has stretched, matter has clumped. Most of the clumps are very far apart. When you lie down at the end of the day and listen to a quiet voice talk about falling into a cosmic void, all of that is already true. The ceiling above you is attached to a building, attached to a street, attached to a country, attached to a planet that will never, in all its lifetime, move close to another galaxy in any way you could feel. You are, and always have been, on a raft floating in a dark ocean whose shores are beyond your senses. Knowing this does not tell you how to live. Cosmology is not a manual. It can say how voids form, how matter flows, how light is shifted and stretched. It can show that the rumor of endless falling into nothing is, strictly speaking, wrong. There is no nothing to fall into. There is only more or less structure, more or less nearby. What it cannot do is translate that into a prescription. It cannot say whether realizing that you are a dense knot in a sparse medium should make you gentler, or braver, or more distant, or more attached. It cannot decide whether the right response is to care more about the raft or to shrug. What it can offer is a change of frame. Before, you might have imagined yourself as one point among countless others in a bright, crowded universe. After, you might see yourself as a brief, intricate pattern in a universe that is mostly quiet. The first picture suggests anonymity. Nothing you do matters because there are so many other stars, so many other possible minds. The second suggests rarity. Whatever a mind is, it does not happen very often. Most of the universe never thinks at all. That shift does not turn you into an exception. It just makes the exception you already are visible. It makes it harder to pretend that structure like yours is the default state, and easier to notice that you are, in some precise and limited sense, a small rebellion against the general tendency of things to spread out and forget. You can follow that thought into many directions: ethical, aesthetic, nihilistic, hopeful. The physics does not care which path you take. It only cares that, for a while, there is a configuration of matter that can think about where it is. If some distant civilization, orbiting a star in another filament, were to map the large-scale structure of the universe and draw a circle around the region of space where the Milky Way lives, they might give it a label. Not because the matter there is especially dense in the grand foam, we are an unremarkable thread, but because, at least for a short time, this is one of the places where the universe has folded itself into stories. Not a scar, not a bug, just a cell in the foam where, between long spans of silence, something briefly speaks. Seen from that imaginary map, the question we began with sounds different. Falling into a void is not about being thrown out of the universe. It is about noticing what the universe mostly is, and what you, for a brief interval, are not. It is about understanding that the background of your existence is not a sea of other selves, but a sea of near emptiness in which a few selves appear and disappear. The video ends, eventually. The screen goes dark or moves on to something else. The room is the same size as before. The planet continues its orbit. The void beyond the atmosphere remains as indifferent tonight as it was before you heard any of these words. Nothing in the physics demands a response, but if you carry one quiet question with you as you drift off to sleep, it might be something like this. If tomorrow I wake up still drifting in this same vast void, still living on this small island of matter in a mostly empty universe, do I want to live any differently at all?